Okay, so the quote of the day today is it's kind of a comic of the day, I suppose. It's from XKCD Comics, comic number 2899. And so we have one stick figure saying when a metric becomes a target, it ceases to be a good metric. And the other stick figure says, sounds bad, let's offer a bonus to anyone who identifies a metric that has become a target, thus making finding metrics that have become targets itself a target. Um, so what's the idea here? Well, I think this is particularly applicable to statistics because a lot of times we have some underlying thing we want to understand. Maybe we're a business and we want to give our customers better service. We want to make our customers more satisfied with their interactions with us or provide more value to them, something like that. So we might identify a metric. We might say, hey, we send out these customer satisfaction surveys, rate your satisfaction on a scale of 1 to 5 or 1 to 10 or something, and we get this number back, and we see maybe on average we're at 3.5, and we say, that metric, that number that I got back seems to suggest that I'm not doing as well maybe as I want to, as I ideally would. Well, then the question is, what do you do about that? And unfortunately, if we make that number the target, if we say our goal this year is to increase our customer satisfaction from 3.5 to 3.8, now that metric has become a target. And that might seem like a good thing to do, right? I mean, if you've ever worked in a corporate environment, these kind of things are done all the time. This is like the standard approach. I would even go so far as to say. Um, So what's the bad thing about that? Well, the bad thing is that for a metric like that, there are typically many ways to what you might call game the metric. One example, and I honestly don't know how historically accurate this is. I've heard this example come up in a few different scenarios, so I'm guessing there's a little bit of questionable historical accuracy here, but the example is a good illustration nonetheless. Uh, so if you imagine that there's some geographic area that has some pest that they want to get rid of, I've heard it like somewhere in Europe with rats, or like India with snakes, or I've heard it a couple different ways. But let's just go with, some European country and they have a bunch of rats and they want to get rid of the rats. So they think, okay, well, what we'll do is we'll offer an incentive. We'll say to our folks, for each, rat tail that you bring in, essentially evidence that you've killed a rat, we'll give you $1. And the idea being, well, if we start compensating people for killing rats, the people will go out and kill the rats for the reward, and we'll reduce the rat population. But the problem is people might figure out that it's cheaper to breed the rats, kill them, and then turn in their tails, and they can make a quicker profit, an easier profit, whatever, doing that than actually going out and hunting the rats. So they can game the metric, right? It's not actually rat tails that we want to collect. It's not actually dead rats that we want. We don't want a bunch of dead rats. We want the rats that are infesting the area to be gone. So that's kind of one example. Like I said, I don't know how historically accurate it is, but that example is often used to illustrate this point. So in a company, if we are interested in increasing customer satisfaction, we probably ought to say, well, that 3.5 isn't what we had hoped it would be. That means we have to do better on customer satisfaction. Let's not target the 3.5 number. Let's try to do better at customer satisfaction, right? Like, what can we do to serve our customers better? And that's a really hard thing to ask people to do, because by removing that metric, by not saying something like, we want to get it to 3.8, like that kind of, that kind of gets rid of the feeling of having a goal or being able to reach a goal or anything like that. So it's very tempting to say, like, let's make this number 3.8, but then, well, can we make the number 3.8 by just being more, let's say, creative about which customers we send surveys to? Can we introduce a selection bias, or make the survey, easier to take or harder to take, or whatever? There are a lot of things that could be done to change that number. Another good example is like a lot of people, especially, right after the holidays, they're like, oh, I want to lose weight, right? It's like, well, do you want to lose weight, or is that really what you want to lose, right? Most people don't want to lose weight unless you're like a boxer that needs to make weight for a fight or something. If you're judging your how well you're approaching that goal by the number on the scale, well, somebody can dehydrate themselves and lose weight really quickly, but that's really unhealthy, right? It's like, it's better to be very clear about what your goals are and not allow the metric to become a target. So I think that's the idea here. I think this is called something like Goodhart's law, and but there's a lot of similar ideas that, roughly speaking, if you make somebody's job dependent on a number, they very well may destroy the company to make that one number look good. So we have to be very careful about setting up proper incentive structures, and when we're doing statistics, when we get a result out, like, how does that fit into the bigger picture? Okay, so again, today, the plan is to continue working through Chapter 2 PowerPoint. Probably finish it up today, maybe not. We might have a couple of slides left over for next time, or we might get through it a little bit earlier than the end of class today. And the Chapter 2 homework is available in my stat lab. So just give me 1 second here to switch my screens around to get the PowerPoint up, and we'll get started. Are there any questions in the meantime?
Is the homework for like, sorry if you can hear me, there's like a lot of people. But is the homework based on just this Zoom meeting?
The homework is based on a combination of the textbook and the lectures. So most of the material in the homework should have been covered in the lectures, but there will occasionally be a point here or there that might be covered in the textbook and that we didn't quite fully address in the lectures. But I think the idea is, the overall idea should be addressed in both the book and the lectures. And occasionally there will be an idea that we cover in lecture that's not in the book, but that's not too frequent.
Okay, thank you.
Yep. Okay, let's get into it then. Let's see. There we go. I couldn't remember my shortcut key to make the PowerPoint go full screen like this and stay on the slide that that I wanted it to stay on. All right, so last time, just to quickly recap, we talked about distribution shapes a little bit. We talked about this first slide, and we said there were bell-shaped, bimodal, and uniform. They were three descriptive terms we might use to describe a graph. So a bell-shaped graph looking something like this, peaked in the middle, tailing off to the two sides, and symmetric about that peak. So if I flip the graph over its peak, it looks the same. Bimodal, having two distinct peaks. And uniform, being straight across or flat. And we kind of said that a lot of things end up bell-shaped, and that's due to something we'll see in chapter 6 called the central limit theorem, that if we average together lots of small influences, the result tends to be this kind of a bell-shaped distribution or normal distribution or Gaussian distribution. So things like IQ, things like weight for people, things like, say, height for people, SAT scores, lots of these kind of things tend to be normally distributed or tend to result in a bell-shaped curve. Bimodal distribution, I think the easiest way to kind of think about this is it's a little bit like two bell-shaped curves lying on top of one another. So for instance, if we think of, say, height or weight, there are a lot of minor influences to height or weight, but there's one major influence, which is biological sex. So men tend to be taller and heavier than women. So if we looked at, say, height or weight for people as a whole population, we might see something like this. We might see kind of the women's group and then the men's group at hitting slightly different peaks, versus if we looked at, say, the weight of men or, say, the height of women, we might see a more consistent, like, single peak, single bell-shaped distribution. I think in reality they probably overlap enough that you're not really gonna see too much of that really bimodal um, distribution in, say, men versus women's heights or weights, um, but you could imagine something like that would be maybe an example of a bimodal distribution. And then uniform, these are often human created. Things like die rolls, things like coin flips, things like roulette wheel results, cards pulled from a deck that we've, gone through a lot of effort to make sure that the outcomes are all equally likely. But we do have some things like, say, birth, sex, uh, that do end up, like roughly 50-50. So there are some naturally occurring things that are uniform. Now, another way that we can describe or characterize distributions is based on what we call skewedness. And skewedness has to do with outliers. So what's an outlier? Well, at this point, we're just going with kind of the colloquial understanding of outlier. We'll have maybe a more nuanced, or at least a more objective look at it later on. But for right now, we're saying an outlier is really any data point that doesn't fit in, more or less, you might say, with the data set. So if you look at a data set as a whole and you say, oh, this data point seems very strange relative to the rest of the data set, that's an outlier. Of course, this is a very subjective thing to say. So we're going to come up with some more objective ways to assess this later on, chapter 3. But uh, we say that a data set is right skewed if there are outliers to the right. So the most common way of seeing a right skew distribution is we have kind of a peak. We have something that actually starts to look like a bell curve. But it doesn't really tail off to, let's say, the right side. Or in practice, what would this look like? Say for a histogram, maybe I have kind of most of my data clustered around one another, but I have like one data point over here, another one over there, something like that. Right? I think most folks would agree that, like, these are kind of like the typical or the normal data points, and these ones kind of seem strange. There's like one data point kind of far off to the right, one data point even further off to the right. They seem like outliers. They seem like they don't really fit in with most of the other data. Since the outliers are off to the right, we would call this right skewed. So the direction of skewedness is the direction where the outliers are. And then for left skewed, we have a completely analogous idea. something like this. Or a histogram that looks something like that. So again, our kind of most of our data is clustered together. And we have a couple of data points that don't really fit in. Now you might ask, like, when does something change from, say, right skewed to like bimodal, right? Like when are there enough quote outliers that they're no longer outliers and represent a whole other component of the data set? Again, that's a very subjective thing at this point. So we're kind of sticking to very clear black and white examples for right now. And those more gray area examples will have more objective definitions later on. Give me 1 second here. Okay, so what are some examples of skewed distributions? Well, the most common examples are financial or economic data that tend to be right skewed. So, I mean, roughly speaking, a person's income is only going to be positive. I guess you could like actually lose money at your job if you open a business or something like that. But for most cases, a person's income is only going to be positive, and most people's income is going to be kind of moderately positive, right? Like, say, most people earn between, 30,000 a year and 150,000 a year. I think that's a pretty safe set of guidelines. But there are a few people who earn like way, way off to the right, like Bill Gates or Elon Musk or those kind of folks. So things like annual income, things like wealth tend to be right distributed. Wealth is a little bit, more complex because you can be in debt, you could have negative wealth a little more easily than you can have negative income. But still, there are people that have wealth, depending on how you define it, that's, say a couple $100 billion. I don't think there are really people that have, you know, negative net worth in the multiple billions of dollars. So because that tends to be right skewed, you have things that are like things that depend on that. Things like, you know, house costs. Well, house costs are going to tend to be, or house prices or values, whatever you want to call it, are going to tend to be right skewed because the people who are making the tons of money want big fancy houses, and everybody else kind of wants houses that are roughly the same as one another. So a lot of financial or economic data is right skewed. What's an example of something that's less skewed? Uh, all the examples that I know of are kind of like a little bit morbid, but uh, things like age at death. I mean, you can make a left skewed distribution just by like taking the negative of a right skewed distribution, but that's kind of, kind of a silly thing to do. But something like age at death, right? Like most people live something like 60 to 80 years ish, but there are some folks who get, in an accident or something like that and die much sooner. Somebody might die, say at, 30 years old from an accident. If the average, say, age of death is like 70, they might die, 40 years younger than typical. But there are very many people living 40 years older than typical, living, to 110 years old. So we might call something like that left skewed. And of course, there are folks who die much younger than that. Uh, nobody's going to live, say, 70 years longer than the average lifespan. Nobody's living till 140 years old. Okay, so that's distribution shapes. And again, these are just some terms that we use to describe shapes of distributions. And these ideas of skewedness and outliers, we're going to revisit that in chapter 3 and look at these a little more objectively, but we're just introducing the idea here. It is pretty subjective at this point. Let's look at some other types of graphs. So another really whole area of statistics is this idea of time series, where we have a graph where the horizontal axis, the independent variable in a sense, is time. So rather than this being a graph of like, you know, bins related to say a person's height and frequency. So how many people are 5 feet to 5'1" tall or 5'1" to 5'2"? This is using time as the horizontal axis. So this is a graph from a previous textbook of major airline accidents from 97 to 2007 and their frequency. With time series graphs, there are a lot of things we have to be really careful about. It's kind of a whole subfield of statistics in and of itself, time series. So we might talk a little bit about it as we go through the course, but I think I'll probably just leave it there. We've already seen one example of this with the S&P 500 data having to correct for that inconsistent units that maybe initially didn't seem like an inconsistent unit. Here's another example of a time series graph. This is from Gallup polls. Unfortunately, they either don't publish this survey anymore or it's behind a paywall. I'm not sure. I haven't been able to find this particular survey for a while, but they're unemployed, underemployed, which is an interesting number. So that's people who aren't employed to the level that they either once were or want to be. And then percent payroll to population. So they used to publish this, I think roughly weekly, maybe monthly. And you can see that on this picture, there are 3 different time series graphs. And going from, say, February 2010 to August of 2015. And the nice thing about time series graphs like this is you can sometimes see a trend over time. It's maybe a little bit hard to see with these lines because they're, they look fairly flat. But if you pay attention to this grid line at 14 here, you can see, for instance, the underemployed line that's in the middle starts about halfway between 14 and 26. So maybe something like 20 or 21% it starts at. And we see over time it approaches that grid line, ends up at around 14 to 15% from 20 to 21%. So roughly say a 5 percentage point decrease on a scale of 20%, the percent underemployed, the underemployed folks have decreased by a quarter over that time period. So it actually is a pretty substantial decrease. Another example of a time series graph, one that we've all seen, is stock market graph of some sort. This is the S&P 500, and we see the big crash from the housing market crash, and then the recovery afterwards. That's why you never really want to sell at the bottom of the market, right? If you sell down here, historically the market has always crashed and then recovered. So after a crash, it has a nice long, steady positive series of gains over many years. And if you sell down here, you don't get to capture any of that, but you captured all of the losses. This is just another version of that graph. And one thing that we always want to be cognizant of when somebody shows us a time series is typically they had to pick a starting time, right? Presumably the end time would be like current time or the most recent time we have data for, but we had to usually pick a start time. We're probably not going to pick the start time being like the inception of the S&P 500 in whatever 1926 or something like that. It's probably not what we're interested in, but I could tell a very different story with this picture versus this picture, right? A boom, a crash, and then a recovery versus, hey, everything looked great over this time period. and that's only the difference of a couple years, right? So the difference of 1 year would look like a crash and then a recovery. 2 years would look like a nice upswing and then a crash, then a recovery, or eliminating those and starting in 2009 would just look like a recovery. Here's kind of a joke for my computer science folks. So if you've ever coded in any of these languages or written stuff on Facebook and so on, like these over time, for whatever reason, these things uh, that start with a crazy symbol, like hashtags or dash and pearl or so on, like seem to get popular over time, and then we revert back to like more normal language, things like C++ and Python, and that are a little easier to read or to figure out what's going on. Okay, another one that we've probably seen before is a pie graph or pie chart. The goal of a pie chart is to make the relative frequencies very easy to see very quickly. So this is an example of actually CCAC's spam filter from several years ago. They sent this around to us one time, and I thought it was really cool. And they never sent it around again. So, um, but I saved it for this course. And you see across a couple of different weeks, they have the amount of daily mail, viruses, amount of spam, and so on. I feel like this was from just my inbox. I don't know. I feel like I get that many emails. Probably don't. And you see that the breakdown here breaks it down to spam, spam high, I suppose, spam medium, the dark blue and light blue sections down here, blocked connections, which I guess is probably somebody trying to go to a website that our our internet doesn't think is safe. Legitimate, the green ones, bulk messages, the pink here. We see that that makes up the majority of them. There's a few like viruses and so on that don't seem to be all that prevalent or other. In fact, we can't even really see their slice in the pie here. They're so small. But at a glance, I can see that blocked connections, high level spam and medium level spam make up 3/4 of what was pulled out by the spam filter. And then for the remaining quarter, about half of it is bulk messages that were pulled up by the spam filter, and about half of that remaining quarter were legitimate messages. So things the spam filter pulled out and somebody went in and said, no, that's a good message, let it through. So this is just to be clear, this is our spam filter data, not all of the emails coming in. I would hope that we don't get that much junk coming in. This is just for the messages the spam filter pulled out. So we can see that about half of what the spam filter pulled out was actually spam. About a quarter of what it, I suppose, did was block connections. I don't know if that's somebody clicking on something in an email and it not letting it go through or what, but whatever that may be. And then the remaining quarter were either bulk messages, distribution lists or whatever, or legitimate. So here's another example. Are you worried about losing your job? 25% roughly said yes, and about 75% said no. We can see at a very quickly at a glance what that proportion is by looking at this pie chart. This was from, I think this was from Rasmussen polls, if I remember it, either Rasmussen or Pew Research. Pretty big pollsters, pretty well established in the field. And I actually, I don't know that there was this report that I read that this graphic came from and a couple others in this presentation, and I didn't really like how this report came out. I don't know if it was like the intern doing this or something, or somebody just had an off day, but to me, this looks really confusing, right? Because I kind of, at a glance, I look at this and I say, are you happy with your job? We're looking at job satisfaction. It seems like a lot of people say yes over here, and not a lot of people say yes over here. It's kind of confusing. So I have to look really carefully, and I'm like, oh, okay, are you happy with your job? 75% said yes, 20, or well, I guess just under 20% said no. Presumably some just declined to answer. And are you worried about losing your job is the question over here. Well, if you're happy with your job, you're probably not worried about losing your job, and vice versa. So, or certainly if you're worried about losing your job, you're probably not all that happy. So in my mind, it actually is kind of confusing because they, in a sense, like switched the direction of the question, but then kept the colors consistent with, yes versus no. So if you're going to use, coloring in a graphical technique, then, use it in a way that makes it easier for people to understand very quickly what's going on, not in a way that makes it more confusing and trips them up. And then they say, wait, what's going on here? And have to look very carefully. If we have to go to that level, then we might as well just present the numbers instead of a graphical representation. And here's another graphic from that same paper. So these kind of, like ring style pie charts just kind of drive me up a wall. I think it's so hard to tell actually what's going on here. So you see that like the job market is better, worse, or the same, and the different rings correspond to different age groups, where better, worse, and the same correspond to the different colors. So we can see that like it looks like 18 to 39 and 65 plus roughly agree that the job market's a little better at, something like what, 25% ish, and maybe 40 to 64 think it's better at a slightly lower rate than that. Basically, everybody thinks it's the same at about 50% rate. And worse, it's hard to tell because worse kind of starts and ends at different points for everybody. So it's actually kind of hard to make heads or tails of what's going on here. And even worse, when you jump over to the other picture, a year from today, unemployment will be higher. Presumably, this is the proportion of folks who said yes or agreed with that, um, although that is not clear. We see now the different colors correspond to the different age groups instead of better, worse, or the same. So again, if you're going to use coloring in a graphical representation, use it to enlighten rather than confuse, right? I feel like maybe this was somebody got a new, got access to a new program or a new set of tools in Excel or something, and was just like, I want to use all of the tools and trying to use all of the colors and the fancy pictures and all that. But sometimes just a basic, well, often just a basic histogram is the better way to go. And I would argue that the better way to go here, instead of this kind of concentric rings pie chart, just going with a standard histogram would be a much better way to go. Have the different ages, and for each age category, have 3 histogram bars, one for better, worse, or the same, or have better, worse, and the same, and then have 3 different histogram bars, one for each age, for each of those categories, something like that. And just kind of a little joke, the percentage of the chart that resembles Pac-Man is the yellow portion. So speaking of the impact of color on graphs, it can be very good, very useful. We saw that in the US population change in each state over 10 years. We saw that with something like, what was it, 510 data points, we were able to quickly glance over the data and actually glean a lot from that instead of looking at 500 some numbers. We also saw some examples just now that maybe where coloring was used to not so great an effect or to a detrimental effect. But heat maps are where we're using coloring to indicate relative values. So here's an example. Somebody ran a ton of simulations of Monopoly on a computer, and they analyzed, if I buy, a single property from the Mediterranean or Baltic group, how many opponent turns does it take for me to pay off that property on average? For Mediterranean or Baltic, it takes about 1,000 opponent turns to pay off that property for me to make as much revenue, as much income, as much dollars in as I spent on that property. So for the first property of one of Mediterranean or Baltic, it takes 1,000 or so. That's a blue number because that's a very high number. That's not good for us. We'd rather have our investment paid off sooner and fewer opponent rolls. We see, for instance, the investment of putting, say, a third house on Tennessee, New York, or is it St. James? I think that's what it is. That only takes about 9.5 opponent rolls on average. So if we're playing with with 4 people total, so there's 3 other people, like I make my investment, and by the time it goes around 3 times, I've kind of on average paid that off, that third house. So that's a better deal for me. That's a darker red. Buying the first railroad, not a great investment, but buying the fourth railroad, a much better investment. So if I've already got 3, buying the fourth, I can pay that off much more quickly. You also see that, buying a single property is much different than buying the last property on the block. If you actually follow the rules, which I don't think anybody has ever actually followed the rules in any game of Monopoly in history, but if you actually follow the rules, you need to get your Monopoly, you need to buy all of the properties in that block before you start building houses or hotels or anything like that. Now, of course, it should be said that in order to access, say, the ability to put a third house on St. James, Tennessee, or New York, or the ability to buy a fourth railroad, I mean, that kind of necessitates that I bought a first, second, and third railroad. So the strategy isn't completely obvious from here, right? We don't just look at this and say, oh, looking at this tells me exactly how I should play the game. Well, what are the chances of me being able to complete this monopoly? Mediterranean or Baltic might be easier for me to complete. It might be less likely that somebody else, buys one of those if I already bought one, and I might be able to access the third and fourth house more easily there, or the hotel there, than if I had to get, say, 3 St. James, Tennessee, and New York, or specifically if somebody saw that I was collecting those and then tried to steal one out from under me, something like that. So the strategy isn't completely clear on the basis of just this chart, but again, this chart could give me some important data to look at. I'm probably not going to invest in Park Place or Boardwalk because even on the right side, those numbers aren't that great. It's just too expensive. I mean, if somebody lands on it, I get a whole bunch of money, but people don't land on them that often, and it just costs a ton of money to buy them initially or to build anything on them. So this might direct my strategy, right? I'm probably going to be a little less likely to try for utilities rather than railroads. It might direct my strategy, but the data doesn't just say, here, do this strategy mindlessly. Another example is this so-called Index of Economic Freedom by the Heritage Foundation. Um, they're a think tank. They certainly have a bias to them. So that should be taken into consideration here. That's another thing. Anytime that we're looking at data or statistics or anything that's presented to us like this, we always want to ask ourselves, well, who's presenting it? Do they have a bias? What direction is their bias? Things like that. And not so much in the sense of bias statistics, but more in the colloquial sense. But that can certainly lead to bias statistics. But this index of economic freedom, we see it's a number from 0 to 100. Darker green means more freedom according to their definitions and metrics, and values closer to 0 get to yellow, orange, and then red. And we can look and pretty quickly look at different regions of the world or different countries and pretty quickly see roughly where they are on this index. Something kind of similar, just looking at the US, the annual mean wage of registered nurses by state. We see that with the legend up here, darker blue represents higher wages and lighter blue represents lower wages. And we see the places like, say, New York, California, Alaska tend to have higher wages. We can pick that out. And in fact, it looks like kind of the Northeast, the West Coast, and Alaska and Hawaii, it looks like are kind of where the higher wages are mostly centralized. And the lower wages seem to be centralized kind of more or less in what we might say is like the Midwest and South, roughly speaking. There's all kinds of, people love to debate whether this or that state counts as Midwest or whether this state counts as South or not. But, more or less we see the lower wages clustered together here. Again, this doesn't mean that, if you're going to be a nurse, that you should definitely go to New York or California and never go to Missouri. I mean, cost of living is going to be a lot higher in New York and California as well. This is just annual mean wage, annual average wage. An improvement to this graph might be something like adjusting for cost of living. So that, if things on average in general kind of cost 30% more in New York than in Missouri, we like divide the New York number by, say, 1.3, something like that, so that we're correcting for that difference in cost of living. So that might be an improvement to this graph. But then again, if you do that, then somebody could argue, well, how are you coming up with that cost of living index, right? There's always something that can be argued. There's no metric that's going to be perfect. But we see actually PA is pretty good. We're in the second highest category. So if you're going into nursing in PA, at least according to the 2021 numbers, decent outlook for salary. Any questions so far? Give me just a second here. I always seem to have like a week or two in the fall and a week or two in the spring where my allergies just kind of go haywire. And it's usually a little later than this, but I guess with the temperature fluctuations and everything, maybe all of the pollen or whatever it is, pollen and dust and ragweed is coming out. All right, so moving on to the next topic, scatter plots. Here we're shifting gears a bit. So before we might have had, say, a histogram, or say a pie chart, or even like a heat map, which I can't draw as easily. But these were describing one variable. So we might be looking at, say, people's heights, 5'5", 5'8", 5'10", and so on. This one variable and looking at its frequency. Or a pie chart, again, looking at one variable, say like spam type, A, B, C, D, E, maybe a more categorical variable. Something that I didn't mention is that a pie chart maybe works a little better for, say, a categorical variable, for one where you just place the categories into bins. There's no real natural ordering or ranking. For something like a histogram, that's often going to work better for something that at least has a natural ordering or ranking. Not all the time, maybe. But I would say certainly for something like a line graph, we'd want ordinal data for that. I think it would be a bit funny to try to make a line graph for something that has no natural ordering or ranking. So again, that, stuff that we discussed in chapter 1 does come into play here. Now, scatter plots are a little different. So scatter plots are relating two variables. So what's the idea? Well, maybe we have two variables, say height and weight, and we're interested in their relationship. So we're trying to look at two variables at the same time and tease out a relationship. So up here for, let's say, just people's heights, I might look at, say, data point number one, and maybe that person is, what, 70 inches tall. Data point number two, that person was 58 inches tall. Data point number three, that person was 65 inches tall, and so on. Maybe I get down to data point 100 and they are 67 inches tall. So this is what my data set would look like. And really my data is just this single list of numbers corresponding to the single variable height. Now, if I want to look at height and weight, I mean, I guess maybe one way I could do it is I could measure a whole bunch of people's heights and then go and separately measure a whole bunch of other people's weights. That might be helpful, but it's going to be a lot better if I can say, look at person number one and measure their height and get, say, 70 inches, and also measure their weight, and maybe I get, 175 pounds. So this is the same person. I got their height and their weight. Now, a different person, I can get their height and their weight. So maybe they're 58 inches tall and 95 pounds. Person number three maybe is 65 inches tall and 115 pounds, and so on. 67 and say 145 pounds, whatever. But the point is that in this setup here, each of these heights and weights is inherently related. This height and this specific weight correspond to the same individual person. This height and this weight correspond to a different individual person. So these are kind of like ordered pairs, like 70, 175. They're inherently linked, or 58, 95. What can I do with an ordered pair? I can plot it on a graph. I can say, look at height and weight, and I can plot, 70, 175 or 58, 95, or I plot all these heights and weights for all these different folks, these, maybe 100 different folks. And maybe I get something like this. And what I can tell right away is it kind of seems like there's a positive relationship between height and weight. And I can't seem to draw it. There we go. Something like that. It seems like I can roughly say that if I observe that somebody is, say, taller than average, I would expect that they would be heavier than average. And if I observe that somebody is, say, shorter than average, I'd expect that they are lighter than average. That seems to be a conclusion that I could draw from this data. How can I kind of see that? Well, one thing I could do is try to pick out like where kind of the middle of the data is. If I imagine each of these data points being like physically weighing 1 pound or something, and I had a flat plate, like where would the center of mass be? Where would the balance point be? Maybe something like here. And if I draw a vertical and a horizontal line, just kind of shifting my axes from 0, 0 up to kind of the middle of the data, I see that there's more data in the first and third quadrants and not as much data in the second and fourth, indicating a positive relationship. Then when one variable tends to be further to the right, the other variable tends to be further and up high. And when one tends to be further to the left, the other tends to be further down. So that's the idea of a scatter plot. We're relating two variables to one another, and each little dot represents one data point. So if we look at these scatter plots over here, this is from the output of a flow cytometer. So if you're interested in medicine, it's a really cool technology. Even if you're not interested in medicine, you can look up flow cytometry and see how it works. Super interesting. Basically, these things, the CD19, CD34, if you look at the surface of our cell, we think of cells as like little basketballs or something, but really they're like fuzzy. They have all these little proteins and signaling molecules and transporters and all that kind of stuff hanging off of them. And these CD numbers relate, they're clusters of differentiation. They relate to whether or not a cell is expressing a certain maybe protein or maybe something else on its surface. So a cell might be expressing this protein, kind of like saying, hey, I'm this kind of cell and I need to take in these kind of resources or have these kind of interactions. So that's what, CD19 would be a certain type of maybe protein that is or is not on the surface of the cell or is on the surface of the cell more for some cells and less for other cells. Same with CD34 or IgG or these scatterings here, forward scattering and side scattering, have to do with shooting a laser through the cell. And like if the cell has a nucleus, the laser is going to bounce off of some big stuff and scatter to the side. Or if it doesn't have a nucleus, say it's a red blood cell, the laser will kind of shoot straight through and go forwards instead of off to the side. Really interesting technology. So if you're interested in medicine or even kind of like physics and lasers and stuff like that, worth maybe a 5-minute lookup on Wikipedia or something. But this is the result that a clinician would get. Maybe an oncologist or a pathologist would look at this and they would say, on the basis of some plots like this and some others, and they would look, see, okay, do I see a lot of cells that are, say, highly expressing both CD19 and CD34? That might put it within this box up here. And that tells them something that maybe says, oh, I'm leaning toward a diagnosis of, leukemia instead of lymphoma or something like that. Or do I see a lot of, if I see a lot of forward scatter and not a lot of side scatter, maybe I think that the cells that I'm looking at don't have nuclei, and that gives me a clue as to what kind of cells they are versus if they do have nuclei or they have other more complex organelles inside of them. That might give them a clue as to, I think I'm looking at these kind of cells rather than those kind of cells. Now, one thing that we see here is that these are really just kind of a bunch of black dots. So if I look at the side scatter and forward scatter, the top left plot, down on the bottom left side of that, it's just like a big black blob. I can't tell if there's quite a few dots there, a ton of dots, or an absolutely humongous number. It's just, a black smear. Same with the kind of CD13, CD34 area here. It's just like there's just a lot of dots there. I can combine the ideas of scatter plots and heat maps and actually say if one dot is really close to a lot of other dots, color it red. If it's really close to quite a few other dots, color it yellow. If it's close to not too many other dots, then color it, blue or green. So the areas that are red have a higher concentration of dots close to that point, and the areas that are blue have a lower concentration of dots near those points. So I can very clearly see, the red mark up here with lots of CD4 and less CD8. These are immune cells that express CD3, CD4, and CD8. I see some red over here with highly positive CD3 and some red down here with strong CD3 and CD4 signals. So I can combine some of these ideas as well, right? And here's another example of a scatter plot. This one's a little hard to read. This is an example that was in the Stanton Glantz book, Primary Biostatistics, that I mentioned at the beginning of the course. And it's one of the textbooks that goes kind of like a half a step further than our course. So again, if you're going into medicine or interested in going into medicine, that might be a book to take a look at. You can pick it up pretty cheaply. But in the Glance book, he talks about this study. So it's an older study. So the graphic isn't, super, super crisp. But if we look at it, we have two variables we're measuring here. We're measuring muscular cross-sectional area for forearm muscles, and we're measuring grip strength for that individual. As folks get older, they tend to lose grip strength. And, we don't usually think about it if we're younger, but the ability to do almost anything in this world requires grip strength, right? If your legs are really strong and your back is really strong, but you can't hold on to anything with your hands, it's really hard to transfer that strength to anything, to even do something like pick up a milk jug or open a door, or if you fall down, like pull yourself back up, get yourself back standing again. So super important thing for older folks to understand what can be done to help their grip strength to keep them independent for longer. So we're looking at cross-sectional area versus grip, and we're actually we did something a little different here as well. Instead of color coding, because this was 1980s and I guess everything was in black and white back then or something. But instead of color coding, they're representing these as diamonds or as triangles versus diamonds. Unfortunately, triangles look a lot like diamonds. I wish they would have picked two different, more different things, the things that looked a little more different, like triangles and pluses or something. But we can kind of see if we look at, like, on the right side, very close to the top, those are pretty clearly triangles. And if we look at the right side very close to the bottom, those are clearly diamonds. So we can kind of tell it apart. We can see that there's like a triangle sitting in amongst these diamonds and maybe a couple of diamonds that are closer up top. And the idea is that we have the normal subjects, who are the triangles, and the patients with rheumatoid arthritis, kind of a joint disease, messes with the joints in the hands. They're the diamonds. And we actually can see it's hard to tell near the left when the cross-sectional area of muscle is low. I mean, if you don't have a lot of muscle, you're not going to have good grip strength, whether or not your joints are good. But if you have a good amount of muscle in your forearms, you kind of, in a sense, have the capability in some sense to squeeze hard. But if the joints aren't working well, then we see that the diamonds, the people with RA, have a much lower grip strength than the people without RA, who were kind of clustered up here near the top. So for the folks with more cross-sectional area in their muscle, they have more kind of potential to grip hard. The RA really interferes with that. And this leads us to say, well, perhaps this person could stay out of a nursing home, could be independent for much longer, could be much safer if we can effectively treat their RA. We might think of that as something that's just an annoyance or an inconvenience, but it really is, an important medical condition for these folks, because it can, again, keep them from falling over, or they might be able to get up after they've fallen over, something like that. And then these two lines here are just these kind of approximate models, kind of like I drew over here. If I wanted to say, if I want to describe this data just roughly by a linear model, by a straight line, what would that line look like? What would the line look like that basically goes through most of the data points? And for the triangle folks, for the ones who are normal, who don't have RA, we see that that line is much steeper. So for each additional square centimeter of muscle cross-sectional area they have, they get a much better return in grip strength than the folks who are the diamonds with the shallower line, the folks with RA. When they increase muscle mass, they don't get nearly the same return in grip strength. So any questions so far? All right. The last thing that I want to discuss is the idea of log-log plots and semi-log plots. This isn't a crucial idea or really even a central idea in chapter 2, but it comes up enough that I think it's worth mentioning. It comes up in medicine often, in finance all the time, and even in computer science. I know there's a lot of folks going into computer science type fields. It comes up in computer science as well. So let's take a quick kind of mathematical diversion over here. This is an aside. And like I said, this is kind of ancillary material. I want to mention it so at the very least you have an appreciation of what these graphs are showing. But if you don't catch all of this mathematical aside, that's perfectly okay. Um, Math 108 is a prereq for this course, and at least at CCAC, we typically teach logarithms in Math 108, so you might have seen this before. But if you didn't take Math 108 with us, or if your instructor considered logs to be optional in Math 108, which is actually somewhat debated among our department, the way the syllabus is worded, it's not exactly clear whether it's optional or not. You might not have seen this. If you haven't seen this, again, no big deal. It's not like an exam question or something like that. Um, but just giving you a little appreciation for these kind of plots that you might see pop up. Note that this plot, so let's look at the previous plot really quick. If I go across the horizontal axis, I see 0, 10, 20, 30, 40 on my tick marks. If I go 1 unit of distance to the right, I add 10. One more unit of distance to the right, I add another 10. Same with the vertical axis, 0, 100, 200, 300. If I go 1 unit of distance up, I add 100. Another same unit of distance up, I add another 100. What's different here? Well, if I go across the horizontal axis, I go 25, 30, 35, 40. 1 unit of distance, I add 5. That seems normal. But if I go on my vertical axis, though, from, say, 2027 to 4361, that's like 1 unit of distance. I've gone up by, say, 2,000-ish. To go the same unit of distance up, that takes me about to 9,000. The same unit of distance up doesn't take me to something like 6,000, adding another 2,000. The same unit of distance takes me to about 9,000. And the same unit of distance again takes me to something in the ballpark of 20,000. What's happening here is this is a multiplicative process. 2,000 doubles to 4,000, doubles to, say, 8, 9, something like that, 1,000. 10-ish thousand doubles to something like 20,000. So each unit of distance that we move along the vertical axis, we're not adding a certain number, we're multiplying by a certain number. So that's what a log scale is. So if I have a relationship like y equals ax plus b, or even if we get rid of the b, just to make it a little simpler, we call this a linear relationship. Y is related to x just by a constant multiple. We could put a plus b in there. That doesn't really change all that much. If I have something like y equals x to the a power, we call this a power function. So something like y equals x squared, y equals x cubed, even something like y equals square root of x, that's x to the 1/2 power. So these graphs, instead of looking like straight lines, these graphs will look something like this, or something like this, something like that. They'll look like curves. Now, there's nothing particularly wrong with curves, but if I was just looking at, say, this right-hand side here, I mean, x squared and x cubed kind of look very similar, but they're pretty different models. How do I tell the difference between them? Or how do I tell the difference between, x to the 1.5 power or x to the 5th power? Or, well, one thing I can do is I can put this on a logarithmic scale. So if I take the natural log of both sides, again, this is where, if you're not familiar with natural logs, not a big deal. But one of the properties of the natural log is if I apply the natural log to both sides, powers that are inside the natural log come out front as products. So I see that the natural log of y is linearly related to the natural log of x for a power function. So in other words, consider that I have some data that I want to draw a scatter plot for, x and y. If I take this data and I take the logarithm of all of the data points, this might give me, maybe I'll call it x tilde and y tilde. So maybe this was like, for whatever I'm measuring, 3.7 and 6.4. Now I have natural log of 3.7. I just go to my calculator, type in ln parentheses 3.7, and it gives me a number. And this is natural log of 6.4. That's my logged data. And I do that's the same for each of these. I just take the natural logarithm of all the x's and of all the y's. And I see that y tilde is linearly related to x tilde. So that means that even though x and y themselves might be related graphically by some curve, some complicated function, if instead of graphing on the axes x and y, if I graph on the axes y tilde equals log of y and x tilde equals log x, it's going to be a straight line. What effect does the different power have? Second power, third power, the 1/2 power. That power is what gives the slope of the line. So y equals x squared, when I put it onto, when I graph it on axes where both axes are logged, represent logarithms, that's going to turn into a straight line, and it's going to have a slope of 2 because that's its power. Y equals x cubed will turn into a straight line with a slope of 3. Y equals root x, or x to the 1/2 power, will turn into a straight line with a slope of 1/2. So the slope of that straight line in a log plot, log plot, if I graph on a log plot and see a straight line, that tells me I have a power function. My original model looks like y equals x to the power, to some power. And the slope of that straight line that kind of goes through most of the data, that slope is the power that I ought to use for my model. I could have lots of types of relations, but I could have a third type of relationship, say y equals b to the x power, and exponential relationship. Well, here, if I take the log of both sides, log y equals log of b to the x, and again, the power comes out in front. Well, now I see if I have x and y, what I use up there, 3.7, 6.4. I see that log y is related by a constant. B is just a constant, it's the base. So log b is just some other constant. But the log of y is related to x itself. So for the y's, I want to log them. But for the x's, I just want to leave them alone. So 3.7 and so on for the x's. 6.4 turns into log 6.4. Again, I just plug it into the calculator, get some other number out. That's my new vertical axis coordinate that I'm using. And if I plot x itself, not x tilde, against y tilde, which is log y, I'll get a straight line. This is a semi-log plot because one of my axes is logged, one of them is standard. So for something like this, here we have HIND3, Haemophilus influenza, part of its genome that you put some enzymes in, it chops up the genome in different ways. You run that through a gel, you put that genetic material in a literal gel that has some kind of porous media, apply an electric current, it pushes that DNA along with some force through the gel, and the bigger strands of DNA take longer to get pushed a certain distance, and the shorter strands of DNA can make it through that porous material more easily. They can go further per unit time. So that gel kind of sorts out the um, the genetic material by size. And we see over here, where did my cursor go? There we go. We see over here that when I plot this on a semi-log plot where this vertical axis is logarithm, represents the logarithm of the distance, or sorry, the log of the base pair, and the horizontal axis represents the distance from the well, we see that it's roughly a straight line. Right? We don't expect to get kind of perfect straight lines in actual data, but this yellow one looks very straight. The red looks really straight. The blue one kind of curves a little bit, but it has a region where it looks pretty straight, maybe from roughly 35 to 45 centimeters from the starting point. It's pretty straight, and then it kind of starts to curve. But I do have a region of linearity here. So that might tell me that if I'm modeling base pairs, in other words, the size of the chunk of DNA that I have, the length of that DNA molecule effectively, that's on the vertical axis, and on the horizontal axis is the distance that it traveled along that gel in this experiment. I think the base pairs are related to distance exponentially, because if I put it on a semi-log plot where my vertical axis is logged, but my horizontal axis is standard, right? 25, 30, 35, 40 on the horizontal axis, that's a standard axis. When I put it on a semi-log axis, I get more or less straight lines. So I think I have more or less an exponential relationship between number of base pairs and distance traveled. So if I travel twice the distance, the number of base pairs in that genetic material is, well, in this case, it would be square rooted, but it's a quadratic relationship. Okay. Not square rooted, it would be to the -2 power. So that's a little bit about log and semi-log plots. Again, like I don't expect that everybody caught all of that. If most of you caught the general idea that there are different types of axes, we have our kind of standard linear axes that are pretty common, but we always want to take a glance at the axes and see if I go the same distance physically on the graph, am I adding the same amount every time? That's a linear axis. 25 to 30 to 35 to 40, adding 5 each time. Versus if I go the same distance, am I multiplying each time? 2,000 to 4,000, 4,000-ish to 9,000, 9,000, 10,000-ish to something like 20,000. I'm doubling each time I go a certain distance. That's a log axis. That log axis, that either semi-log plot or log plot, tells me that something non-linear is going on in the background between my actual variables. Okay, and the last thing we'll talk about is misleading graphs. Similar to the end of chapter 1 where we talked about misleading statistics, Misleading graphs, it could be a result of malevolence. It could be somebody intending to mislead you. It could also just be a mistake, right? So just because you see a graph that's presented by somebody that you trust, or if you think that the graph they're presenting actually weakens their argument, so they wouldn't have a reason to present this in a misleading way, that doesn't mean it's correct. They could have just, flat out made a mistake. So one thing that we can see is if we look at something like this, Apple versus Microsoft's revenue, at a quick glance, it looks like Microsoft absolutely blew Apple out of the water in terms of their revenue for whatever year is under consideration here. But if we look more closely, we notice that the vertical scale is kind of a funky scale. It like starts at, this is in millions of dollars, so 65,000 million, it starts at $65 billion and goes up to $71 billion. That's kind of a strange scale, especially considering that revenue, the amount of money that we bring in a year, we probably consider that ratio data, right? If one company brought in twice as many dollars as another company, their revenue, their measure of that would be twice as large. Or if a company brought in $0 in revenue, they had no revenue that year. So this has a true zero. This is a ratio scale. This would be a more faithful representation, this graph, if I started my axis, my vertical axis at 0 like this. Now, if this was, interval data, there's no true zero. I mean, I have to pick somewhere to start. It's not so important that I start at 0. But for something like this with ratio data, we probably want to start our axis at 0. This is going to be a more faithful representation of the data. Most people are going to naturally understand this at a glance much more accurately than they're going to understand this. People are either going to be thrown off, or they're going to have to look really carefully at the axes. And again, if you're making people dissect every little piece of the graph to understand what's going on here, why are you presenting a graph and not just presenting the original data? The purpose is to make it easier to consume. So we want to make it easier to understand at a glance, and we want to make sure that understanding is reasonably accurate. So this probably tells a truer story in most cases. This was something that I saw in a write-up on a blog post or a post online. The top 10 most read books in the world. And if you just look at the picture, you're like, oh, okay, the Bible is about twice Mao Zedong. Harry Potter is a little lower. And, Lord of the Rings, The Alchemist, Da Vinci Code, these are all about the same level. But actually, to give them credit, I did kind of erase some of these numbers, but they did have the scale and everything on here. But the thing is that they're starting their 0 way up high. They have like kind of the title of the book below the axis, below the horizontal axis, and the 0 starts here, and then the top of the book kind of extends upward. So we see actually the Bible's number is 3,900. Mao Zedong is 800, so about 1/5 as much. Harry Potter is 400, about half of Mao Zedong. Lord of the Rings 100, about a quarter of Harry Potter, right? But having this bottom piece with the name of the books, really the graph is in direct conflict with the numbers. So, I'm getting something from the graph and I'm getting something completely different looking at the numbers. I have to take the time, step back, say, wait, all right, what's going on here? Again, maybe not the best graphical technique to use here. There's this idea as well where when we look at a certain thing, we kind of judge its size by its two-dimensional area rather than its, one-dimensional dimension. So if I say something like, I doubled my sales from year 2014 to 2015 from $30,000 to $60,000, and I represent that with a circle with diameter, say 1 unit, versus a circle with diameter 2 units, well, I have actually just doubled the diameter, I might argue that, I'm doing something like, something like a proper histogram, something like this, right? If one revenue was double the other, the bar would be double the height. One sales number is double the other, my circle is double the height. But the thing is that I can scale a bar one dimensionally, and that doesn't scale the other dimension. If a bar is twice the height of another bar of equal width, it's also twice the area. But if I double the diameter of a circle, I kind of double it height-wise, but also double it width-wise. So I kind of end up with 4 times as much, right? I end up with 4 times the area. So, and that's going to be hard for somebody to interpret accurately. Now, as a side note, this idea of circles can be, circles representing numbers can be done very well. And a lot of stats programs these days actually do have these kind of scatter plots where they have circles representing sizes and so on. But they're careful to scale the diameter by the square root of the change. So if one measure is twice the other, then the diameter of the bigger circle will be square root of 2 times the diameter of the first one. So that we scale one dimension and the other dimension, square root of 2 times square root of 2 is 2. So then it's the area that's doubling. Some other misleading graphs, often in time series, we see what I'm kind of saying here is fundamentally different data presented in the same category. So for instance, our S&P 500 data with the inconsistent units, it's in dollars the whole time. So at first glance, it seems like the same unit, but a dollar in 1926 was very different. You could buy a very different amount of stuff than a dollar today. Things like detection bias. This was another example from a textbook that we had used in previous years. Leading causes of death for men, 25 to 44, over the years 1984 to 1994. And we see several different causes here. We see things like accidents going down, deaths from cancer going up. And the big thing we see is that deaths from HIV went way up. Now, at a glance, we might look at this and say, oh, okay, like fewer people were dying of accidents 10 years later, more people were dying of HIV 10 years later, slightly fewer from heart disease, slightly more from cancer. But again, we have to be careful over a span of 10 years. It's not just the amount of people who die from these things that necessarily have changed, but also a lot of other things have changed. For instance, what was our ability to detect cancer getting better over that 10 years? Somebody who might have died just from, quote, natural causes in 1984, if they had better detection methods for cancer, they might have had their cancer detected and then died from it. And now it's attributed to cancer, where they would have died from cancer in 1984, but we just wouldn't have seen that to call it cancer. We'd have just said natural causes. Or same with HIV, right? If everybody knows to look for this, maybe people were getting tested more often, people were learning that they're positive, and then at that point, I don't think the treatments were very good. We have much better treatments today, I think. But at least the person, knew what they had. But then whenever they died, that death was attributed to HIV instead of just natural causes or an infection or something. On the other hand, accidents have gone down over this time. What's the detection bias for somebody dying in an accident? Not much, right? If somebody's in a car crash and dies, you can assess that accurately in 1984 or 1994, or if they're in a construction accident and die, 1984 versus 1994, you're probably not going to get better at figuring out this person died in a construction accident or in a car accident. So accidents went down, probably because, in part, we're not really manufacturing as much anymore. We're moving towards a service economy over this time period. And also there is no increase in the ability to detect. Why did cancer go up? Well, we were probably getting better at treating cancer and getting better at detecting cancer. And maybe the background of cancer actually did go up. Maybe it didn't. Maybe it got better. But if we're getting better at treating and better at detecting, and there might be a change in the underlying amount of cancer, like there are so many things being thrown into the pot that it's really hard to tease apart why this number went up just a little bit over these 10 years. So that's something we have to be really careful of in time series when time is the independent variable or the variable on the horizontal axis. We just have to be really aware that, over the span of 5 or 10 years, or certainly 100 years, a whole lot can change over that time period. Uh, just as kind of a general rule, I tend to choose the simplest graph that gets the job done. So this is an example from a fairly highly regarded pathology textbook where they had a picture that they were presenting. It was very similar to this one, not exactly the same, but I tried to recreate it as accurately as I could in Excel. And they were looking at non-diabetics versus diabetics and no previous, say, heart attack versus previous heart attack. And this was something like the person's risk for having another cardiac event, say, within 5 years. So it basically looks like people without a previous heart attack, who's also not diabetic, it's 0. Without a previous heart attack who is diabetic versus with a previous heart attack who's not diabetic is about the same. Something like a little under 15%. And people with a previous heart attack and who are diabetic is something like a little bit under 40%. But then they also had a table presenting numbers, and non-diabetics in their prior MI was 2. Diabetics prior MI was actually a little above 40. I thought this was kind of strange until I realized, that there's a parallax here. They did this 3D histogram to make it look cool. But if you notice at the very bottom, say the bottom right edge of this tall block here, it's pushed forward from the kind of back wall. We're also looking with a perspective where we're looking from the top right down to the bottom left. And if you've ever like been sitting in the passenger seat of a car and look over at the speedometer, or you like look at a clock from kind of off to the side, there's this idea of parallax where when something is moved forward from from its whatever, from the back wall or whatever, that where the measurements are, if you're looking from the side, it appears that, if you're looking from the right side, it appears that the measurement is further to the left, and vice versa. Since we're looking from the top and it's pulled forward from the back wall, it appears that the measurements are actually lower than they actually are. So if we take these same blocks and set the gap depth to 0, pushing the block straight against the back wall, we see that we get a more accurate representation. We see that 2% chance for the non-diabetics in their prior MI. We see the 41% chance for the prior MI diabetics. Is this a hugely important difference? Probably not. Is it going to change, any physician's practice going from 39 to 41% chance of, future cardiac event? Probably not. But it's just the point that, why use some crazy 3D blocks kind of thing when you could use just a basic histogram and it will be accurate without having to go through all of this extra analysis and thought and, making sure everything lines up correctly. So these are the references for the different things in this presentation. Are there any questions on any of this? Any questions on chapter 2 so far? Okay, so we have about 9 minutes left. I don't think that's enough time to get into the Excel intro. We'll push that back to next time. We're running a little bit ahead of schedule, so that's pretty good. So we have plenty of time to discuss Excel next time, look at creating graphs in Excel, and then we may even start into chapter 3, depending on how quickly that all goes. So let me stop the recording.